Okay. All right. Sorry for the delay. We're about to begin. Thank you, everybody, for joining us. We have a full house here and then a full house online. My name is Paul Skelton. I'm the vice chair of the U.S. board for IABSE. And we're very, very happy to be hosting Moxon today for their presentation, which I'm certain you will enjoy. A quick note about IABSE. IABSE was formed in 1929, had 49 members in 14 countries. The organization now, which is focused on the advancement and furthering of structural engineering worldwide, both in buildings and bridges, is 3,000 members strong with 100 countries. And the U.S. Contingent is growing, and we try to support events like this and others through the year. And we are very interested in having new U.S. members, especially younger members, to investigate the organization and potentially become members. With that, I'm going to hand it over to Ben and Ezra of Moxon. And
thank you very much, Paul. That's brilliant. Thank you. Yeah, thanks for that introduction. I'm having to use the mouse to control the screen and then my other hand to control the laptop. So bear with me if I get in a bit of a tangle, but hopefully I'll be able to kind of write it as we go through. So my name's Ben Addy. I'm the managing director of Moxon Architects. We're based in London and also in the Highlands of Scotland. We're quite unusual as a practice to have very urban location and very rural location. We're also a very unusual practice in that we do conventional architecture, so buildings and product design and what have you, and you'll see some examples of that. But we also do bridge design, which is obviously the reason why we're in this room with you today. And key to that is my good friend and colleague Ezra Groskin here, who shares a background in bridge design and bridge architecture with me. So I don't know if you want to add a few more words. Or...
Yeah, as you might recognize from my accent, I'm originally from the US, so this is sort of like coming back for me. But I've been working in London for 15 years, kind of exclusively designing bridges, and then I joined Ben about 8 years ago to continue that work. But quite special to be in a small practice that does bridges and buildings, which is a balance I was looking for. And I think you'll see kind of whether we're working on a bridge or on a building, we bring the same kind of interest in design and interest in solving puzzles and interest in how things are built. All these things you'll see through the lecture, but those are things that are important to both of us.
Well, by way of introduction, well, first of all, thank you very much to Hardesty and Hanover and Paul for hosting us here today. And what a wonderful place to be. I mean, we're, like I say, based in London and the Scottish Highlands, so being in New York for a week is a really kind of radical and welcome change. This is the slide that I used to actually introduce an IABSE lecture that I gave last year in central London, their annual lecture for the British or the UK group. And the subtitle for this should be How to Lose Friends and Alienate People. I'm in a room full of bridge engineers. And yet, no one should be interested in the design of bridges. The reason I show this slide is for the last 20 years or so, I've been taunted by university friends of mine who are architects, but it's fair to say they don't share the same passion for bridge design that Ezra and I have. But what they always miss out is the second part of the quote, which is the punchline, really, which is worry about the problem and you'll find the solution. And it's a great quote, and it's a valuable provocation for any designer. It's just unfortunate that bridge design is used as the kind of the basis for the metaphor, because I think that bridge designers, whether from an engineering or an architectural background, are first and foremost problem solvers. It doesn't matter about the discipline you're in. We're all together as a single team working on the same kind of ultimate objective. I should also say that this gentleman in the left-hand corner is probably, he's been called the most famous architect, or rather the most important architect of the 20th century that no one's ever heard of. It's a guy called Cedric Price, and I'm going to come back to him in a moment. But first of all, I just want to talk about probably the most important diagram of my professional career. and probably everyone in this room, in fact. So this is the hockey stick, which doesn't need any introduction, I don't believe. I was in my RIBA Part 1, so the beginning of my undergraduate at university in Edinburgh, when this graph was produced. Now it shows the global temperature variation or anomaly, plus or minus 1 degree for the last 1,000 years, so the last millennia. And of course, the implications of what it describes are so much more profound than just a change in temperature. It's the defining image of our generation and the context in which all of us as designers are working. Back to Cedric Price. So I said that he was the most important architect you've never heard of. He was a teacher and a provocateur. He taught at the Architectural Association in London. He did lots of unbuilt projects, from a thing called the Fun Palace in East London through to various kind of, sorry, I got caught up there, through to various structures which were built, not many. This is his most famous built work, which is the Snowdon Aviary at London Zoo. It's named for the client sponsor, which is Lord Snowdon, who's a photographer. But it was designed by Cedric Price with an engineer called Frank Newby, who was a very famous kind of mid-20th century English engineer, an extraordinary engineer, in fact. Now, the aviary employs principles of tensegrity, so much like an earlier project by Frank Newby in London called the Skylon. So it's using tension members and compression members to try and make as light a structure as possible. And in fact, Cedric Price, although he probably wouldn't have admitted it at the time, given his quote about bridge design, was operating in the same way that a bridge designer operates in designing this building. So looking at lightness, looking at efficiency, leanness, making do with minimal materials to achieve an extraordinary building in the end. Apparently Joe's Pizza's here. Now, the other thing to say about Cedric Price is, and you can probably tell from an image like this, is that although he isn't that well known, he's been enormously influential in generations of architects and engineers that came after him. So in New York City here, you've got obviously buildings by Richard Rogers at WTC, you've got Lord Foster buildings all over the place, you've got Renzo Piano's New York Times building. All of those buildings follow from the teachings of Cedric Price back in the 50s and 60s. So there's a kind of an effect that he has caused that is very much present in today's architecture and structural design. And I think the effect is something to do with economy. And now we're going to sort of talk about some of our work and what this means to us as architects and designers. It's how Ezra and I often talk about the work of our practice. It pretty much goes unsaid in our studio, but when we look around what we're doing, both as individual designers, but also collectively as a practice, it's the common thread. So it doesn't matter whether it's a building or a product or a bridge or whatever, it's this idea of economy that is kind of stringing everything together. It's not about being kind of mean or parsimonious, you know, it's about efficiency and elegance. That makes sense. And I think that it's fair to say that we've learned that culture from bridge design. So from working with bridge engineers, that's where we get this idea of economy from. Because in bridges, economy is what we're always striving for. The best bridges are always the most economic in terms of material use, slenderness, lightness, elegance, all of that. So we've sort of split this presentation into 3 ways of thinking about economy. Now, the first one is economy of material, which is kind of obvious. It's using less material to achieve a particular objective. And it's kind of axiomatic for bridge designers. Yeah, it's part of our kind of philosophy and our culture that we're all working with. The second one is economy of action, which is a little bit more cryptic. And this is something that we've come up with ourselves, but basically as a designer you sort of pick your battles. You know, what's important, you prioritize where you're going to focus your energy and your kind of effort, and in our case as architects, it's about targeting those aspects of a design that can elevate what's basic and functional to something really kind of valuable and beautiful. So you prioritize your approach. And then the third and final kind of mode of economy, if you like, is economy of purpose. Now, this can relate to a detail. So I think everyone here as designers will all know the satisfaction when a design can do two things at the same time. You know, this idea of killing two birds with one stone. So on this bridge, in fact, which we'll talk about in a moment, the deck is also a belvedere. So it also is for getting from A to B. It crosses the River Thames, but it's also a means of spectating on the Oxford-Cambridge boat race. So it does these two things. And that's, I mean, what was one of the most wonderful things about bridge design is their instrumentality. So like a product, it has to do a thing, a particular thing. And every bridge in the world does a particular thing, and it does it in common with every other bridge. It goes from A to B, or to C to D and to E as well, maybe. Whereas buildings are quite complicated things. Yeah, they do tons of stuff all piled up on top of each other and can become quite complex objects. Whereas bridges are, this instrumentality means that they are pure design. You still worry about context, you still worry about history, landscape, all of that, but they're ultimately, at the end of the day, they're doing a very pure thing, which is a really kind of beautiful way of thinking about design. So that leads me to our first project, which is not a bridge. Eventually, I'll get to the point and start showing some bridges. But it was designed with crucial input from an engineer. Actually, in this case, from Covey in London. Now, we work, like I said, we do buildings and all that sort of stuff and products like this. But invariably, we're working with engineers who have a bridge background, and that's really important to us. Now, this glorious photograph by a UK photographer called Tim Saw, and it's of a drinking fountain that we won in competition for the Royal Parks in London. It has a New York connection because it was sponsored by Tiffany Jewelers. And now Tiffany have paid for these things all over London's parks. So they're all over the place in the Royal Parks in London. Tiny little things, only about this big, but you know, blink and you'll miss it. But it's like a calling card. They're all over London. And most of them have our name on it, which is rather nice. Now, it's won in, like I say, an open international competition, and it's the first of two examples of industrial design that I'll share, because it encapsulates this idea of economy of purpose. So it does the thing that it's supposed to do, which is deliver clean, hygienic water, but it does several other things at the same time. To all manner of users, canine and otherwise. So there's a dog bowl at the base, which is the overflow from the top. So it drains down into this dog bowl at the bottom before it then goes into the sewer system. That's also a trap. So if someone drops their wedding ring in the top, it'll go down the funnel and it'll pop out the bottom into the dog bowl. You might need to clean it afterwards. But it's this idea of, like I say, achieving several things at once. It's also a bollard. So this thing can be used as a vehicle restraint bollard. So the way in which it connects at the bottom is kind of integral to that. So it can stop a light vehicle. And you can here see the kind of the refinement and the geometry, which is really important to us. You've got this one single form, which, you know, is the mounting for a faucet, for the tap. It's a bowl for splashes. You've got the drain. You've got the sleeve connection from the base. Excuse me. The design is tap agnostic, so you can fit any tap that's available on the market onto this thing, which is really important for longevity, so that, you know, as tap technology develops, you can put a new, you know, infrared tap on the top or what have you. And again, that's something we've taken from that architect at the beginning, Cedric Price, who had this idea of flexibility in use, which is really important. And then we're interested in aesthetics as well. So the form of this thing is really important. It was one of our first forays into rapid prototyping, which is obviously common in what we all do now, but this is like 15 years ago. And this was kind of novel for us. Are you able to? Yeah, that's probably better. Yeah. Right, we're going to team effort this. It'll go a bit quicker now. So this is the actual master part that was milled from the material that then went into form the lost wax casting. So this is in a bronze foundry in Wales in the UK. And you get this incredible kind of beautiful bronze piece that comes out at the end of the casting process. You polish it up. Here's our first customer in the Royal Parks. And then it patinates over time. So the weathering, the way this material behaves over time, again, this comes back to bridges. It's exactly what we think about all the time. And then here's one of them outside Kensington Palace. I think there's about 3 or 4 in Kensington Gardens now, but like I say, they're all over London. The dog's just been at that one 5 minutes beforehand. This is our first bridge of the afternoon. So that's our kind of design philosophy in a nutshell through that project. And I think hopefully, yeah, there we go. So this, Duke's Meadow Bridge. So this is a footbridge in West London that we designed with Covey. So we work with various engineers, and we're really keen to be working with yourselves, both in the UK and ideally in the US in the near future. But you'll hear me talk about various engineers that we work with throughout, because it's always a team effort. It's never about the architect says this and someone else has to make it work, or vice versa. It's always a team effort. This bridge doesn't go across the Thames, it kind of runs alongside the Thames, and it fixes a link of what was a previously broken Thames path that runs along the river. And the second of our bridges to do this, actually after another one in East London. But here you can see the parapet is the primary structure, which allows us to kind of thread this thing underneath the existing bridge and still maintain clearance between high tide and headroom underneath the arch of the bridge. You can see in the plan here how, I mentioned about the belvederes on the bridge. This is the one where just the widening of the corners there enables people to kind of congregate on the deck. See, get this amazing view up and down the river. It's also a perfect location to watch the Oxford-Cambridge boat race. This isn't the boat race; these are amateurs. But you get the idea. It provides this new space in the city, just from otherwise a very functional link along the river. Some more views of it. So you can, you obviously identify this as it's a very, very simple truss, but we're using the truss as the handrail and the restraint all at the same time. So the structure, the parapet, everything is one piece, which again is about efficiency. Now, each part of the bridge was brought up the Thames from Tilbury Docks in East London. So it was floated above the piers, and then as the tide, so the Thames is tidal at this point. So as the tide rolled out, the deck was lowered onto the pier. So you let nature do the work, which is the most efficient thing you can do. Of course, it's not quite as simple as all that, because while we're relying on gravity, we also relied on a particular bit of temporary works that was designed by the engineer, a guy called Chris Murphy, who designed this 3-part locator pin, which is a component on top of the pier, without which this bridge would not have ended up in its perfect final location. It's somewhere in this photograph, and no one who uses the bridge is aware of that, but we're aware of it. And if it wasn't for that locator pin, the bridge would have been very different. And again, these are engineering, bridge engineering in particular, is full of these kind of stories of ways of achieving things in construction that could not have occurred without that kind of genius going on. So it's a privilege to be part of that kind of conversation with architects. Now, the next bridge that we're going to show does legitimately go from one side of something to another. In this case, it's the Royal Victoria Dock in East London. We love getting involved in drawings like this. So this is a drawing where we're looking at the constraints of a structure. We're looking at navigation channels that we need to maintain, the landing points. There's discussions with both structural engineers, civil engineers, and also mechanical electrical engineers, all involved in this one drawing. This is where we're trying to tease out, as a team, we're working on this drawing together to work out what's the best alignment for this bridge. You can see this Excel Centre at the top, there's a new development at the bottom, basically going to be thousands of new homes on the bottom right-hand corner. big development going on. And then in the top left-hand corner is where there's a new train station. And people need to get from one to the other. So that's what this bridge is for. So A to B, straight route would seem to be the most logical thing. However, the blue lines in the middle, we need to maintain an infinitely high navigation channel. So we need an opening bridge. If we have a diagonal line across that channel, then that's quite a long opening section. So you want to come as square as possible to it, as perpendicular as possible, to minimize the cost. And the cost of the opening section is way more than the cost of the backspan. So hence these kind of studies, this sort of exploration. And eventually we arrived at this kind of form, which although it might seem inefficient, is actually not that much longer than a straight line, but crucially it has a perfect or nearly perfect perpendicular open section, which keeps the cost down. So this structure was granted planning permission earlier on this year, and we've got the contractor is on board now. So I think construction is going to be starting
This year
at least. And you can see here the opening section that we're talking about. So very, very straightforward. I mean, I'm in a room full of the absolute experts in opening bridges, so I need to be careful what I'm going to say. But you can see that it's a twin bascule. Each leaf of the bascule rests on the pier itself, so you don't need to worry about locking pins in the middle necessarily. The axis of rotation is the axis of the span leading up to the opening section. So it comes as quite a surprise when this thing opens. It'll have this kind of twisting effect, but actually the mechanism and so forth is really sort of straightforward and simple. And simplicity and kind of appropriateness and pragmatic kind of approach to design is really important. And for us, the joy is in the detail. So this is where you can see these are the actuators. So the rams are in this image on the pier. The little orange bit is where it rests, kind of the bearing when it's in the closed position. The bridge is part machine, and it's quite enjoyable to sort of express that. The design doesn't hide it. And you can see the kind of the S curving trajectory of this bridge. The V piers in the foreground. It's a bit of vertical curve. So as you go onto the bridge, you are climbing, and then you drop down against to allow smaller river craft to go underneath it. So you've got this kind of that's the new development in the background, which has got it's actually quite similar to Hudson Yards in a way, in terms of the focus on landscape, and we're taking the landscape finishes all the way across this bridge. So it's an extension of the urban realm, but you've got this amazing machine underneath it. Okay, so just briefly on another opening bridge. Now this time it's in Dublin, in Ireland, where the port has got this amazing boom in business after Brexit. So once the UK left Europe, instead of all European stuff coming into the UK and then going to Ireland, it's bypassed the UK and goes straight for Dublin. So the port is incredibly busy, and as part of that, they need new road links across the river, which need to be opening links because all the other bridges up the Liffey are also opening. So you can see here it's a bascule bridge with a counterweight. So again, nothing unfamiliar. And there it is in the open position. But sharp-eyed amongst you may have noticed that there's something slightly unusual going with the pivots, particularly of the counterweight arms. So that gives the game away. So this is another piece of kind of ingenious design, and there's one of our colleagues in the office, a chap called Richard the Bridge, which is the most appropriate name for a bridge designer. And he had this idea that if we actually introduced another fulcrum, so if we introduced another pivot, so another pair of pivots, and brought the fulcrum of the counterweight forward of the hinge of the deck, then that would mean that in the opening sequence, the effect of the counterweight would be felt far earlier in the opening sequence than if it were just fixed like this. Does that make sense? So it's actually a more efficient, in terms of energy, it's more efficient opening sequence for the bridge. Plus, obviously, you've got the kind of the drama of this sort of scissor movement that's going on. Yeah, I mean, there's always this kind of joy in the detail of how these things all come together. I mean, there's a whole, we could spend a whole afternoon talking about the design of this. Yeah, it's making sure that everything nests perfectly. Again, this is the stuff that you guys do for your.
Is there rotation in the wire?
Yes, there is. Yes, there is.
The port ends.
Yeah, yeah. So it's a little bit more. Now, in the closed position, the counterweight is obviously also a demonstration of mass and energy, you know, hung above the carriageway, forming a portal. So it's important that this bridge is a gateway both along the river, but also a gateway along the bridge for the port. Now, I think we are still exploring the use of granite as the material for the counterweight. So rather than using steel or concrete, there's obviously carbon savings to be had there. So we'll see where we get to with that. So the second category was economy of action. And I think for architects, are there any architects in the room? There's one, two, okay. There's at least four of us who are architects. And I think that that this is the bit that it's certainly in terms of bridge design, this is probably, I mean, I don't like to sort of divide it into disciplines because I think it's kind of false, but this is probably the bit where as an architect, you probably do have the most potential for impact in bridge design. And it's about this idea of sort of picking things that can just be turned or twisted or changed just subtly, and it can have an enormous impact on the appearance of a structure. So the first example here is this really modest foot and cycle bridge called Hamsway near Worcester in the Midlands of England. You can see even from the drawing, it's a very straightforward brief. It's basically just get around a busy roundabout. And in the elevation at the bottom, you can see it's just a very simple tied arch. It's no different to hundreds of other bridges that cross the trunk roads of England, excuse me. And indeed, the brief from the client was that it should be like other similar bridges. But what makes this not normal are some very, very simple, modest moves in the design that elevate the appearance above its more functional utilitarian brethren. Firstly, you can see here that the parapets lean in the direction of the cycle traffic. So this is a cycle bridge. So hundreds of cyclists today using it as part of a national cycle route. And just that subtle shift changes the perception of the bridge, that someone has thought about it, there's some craft in it, it's relating to the direction of travel. The approach spans couldn't be more simple. So that's on the left-hand side here, is the approach viaduct. It's just a series of columns and some beams and then some edge beams. And then on the right is the arch truss. But to unify them, you can see the outer chords, the square hollow sections have been rotated through 45 degrees. So very, very simple move, but when you see it in reality, that has changed the appearance dramatically. So you get this kind of thin edge, you get light and shadow, and the way in which all these pieces come together takes away from what could otherwise be quite a dull structure. And then these two things come together at the springing point of the arch, or the main span on the right, and then the viaduct back span on the left. You can see where these things don't quite meet one another. So again, it's about expressing the difference between these two parts of the structure, but it's doing it in a really kind of, we think, beautiful way. Hopefully you'd agree that it's, you know, somewhat more elevated from a basic structure. Now the same team, again working with these again colleagues with Covey on another bridge near Worcester, this time across the River Avon. The way in which landscape and bridges come together are really important, I think, for all of us as designers. The bridges can have such an important impact on their settings that you always need to be sort of considering them in landscape terms. So at the other end of the spectrum, I was going to talk about 3 of our viaducts for HS2. HS2 is the UK's high-speed rail network currently under construction. And we are part of one of the 3 very large contractor consortia building the line. So EKFB, Eiffage, Kia, Ferrovial, BAM, they're some of Europe's biggest construction companies. They've had to team together to build this one bit of the line. And then we're working with Arcadis, CETEC, Covey as engineers. And then there's little old us at the end. And we're like the smallest possible cog in this absolutely enormous, enormous machine. But our clients, it's great to their credit that they have brought architects and our engineers and pushed us right to the front of the process and made us kind of instrumental in getting consent for all these structures. I don't know how many of you've seen Ian Firth's TED talk on bridge design. So Ian Firth is former president of the Institution of Structural Engineers in the UK and chair of the UK's IABSE group. He gave a really brilliant talk, and in it he said that a badly designed and executed bridge is nothing short of an act of vandalism on the landscape. And 2 of our viaducts that we're doing for HS2 are located within what's called the Chilterns Area of Outstanding Natural Beauty. So I've had Ian's words ringing in my ears for several years now as we're designing these structures. Now, one of these viaducts is in the Missenden Valley, which is this kind of, you can see in this topographical map, you've got the kind of pronounced diagonal line there is the what's called the Chiltern Escarpment. So there's a series of chalk downland hills, really, really, really beautiful. You think of England, you're thinking probably of this landscape. And HS2, the railway, is cutting through this kind of narrow gap that you can see near the town of Wendover. And we've got a series of viaducts that kind of help to carry the line north through that gap. The first of them being Wendover Dean. So you can see here parallel lines of communication. You've got a railway, a road, there's high voltage lines, power lines, everything kind of runs through this valley. So it's no coincidence that the new railway is coming through here as well. And what this diagram shows is the position of the viaduct, which is the solid orange line, and then the kind of grayed out area to the right with that contour. So that contour is at the same height above sea level as the bridge deck. What that means is that if you're in the grey area, you're looking down on the structure. And if you're in the white area, you're looking up at it, but against the terrain. So this is not like, you think about a viaduct like Milau, which is on one of your slides at the start, amazing structures that stride across the landscape against the sky. This isn't that at all. This is a viaduct that is sitting within the landscape, and that has a really profound impact on how you design such a structure and what's important. So you can see here that it's a pretty simple design. It's a composite or a double composite viaduct, so using steel and concrete in concert with below deck structure. Now, during the petitioning stage, is what we call it in the UK, but when HS2 was a bill in Parliament before it was made an act, the campaign to protect rural England, who are a very powerful stakeholder in the UK, said that the design of this viaduct would be a litmus test for the quality of design on HS2 as a whole. So again, no pressure. So bearing that in mind, we do all the things that you think of as a bridge designer in terms of how this thing sits in the landscape, the span to depth ratio, how's it going to respond to the landform? Can we keep this thing nice and symmetrical? Or we do something like this. So this is actually the employer's reference design that we were given as part of the brief. And you can see that this bridge could be anywhere. It's asymmetric. It doesn't really fit the landscape. The abutments are really crude. There's no real kind of sympathy for what's around it. So the simple thing is we bring some symmetry. You rearrange the structure. You reduce the length of it. Make savings there, carbon cost savings. Simple things. Shortening the structure at one end reduces cost, obviously. But then even better, we can reduce carbon if we can replace that span with embankment. And you'll see that we've kind of eliminated the clutter from the abutments by basically turning them into a socket in the hillside, so a sleeve, so the bridge disappears into a sleeve. See in the animation here. So although this is a really simple structure, it's just a viaduct sitting on piers. If you focus on these details around, you can see the pier heads as well, which extend beyond the bearing shelf. Focusing on these details, you can elevate this thing from being what could be quite crude, quite a kind of rude intervention in the landscape, into something really kind of simple and elegant. And the color of the steel, the way that sits against the rural landscape, the way in which all the landform is dealt with, these are balancing ponds at one end. You know, all these things come together. It's not so much about creating a statement or an icon or anything like that. It's about just being kind of crisp, minimal, polite, you know, worrying about proportions. You can see these piers where we have sort of extended them beyond the bearing. So this is about accentuating the bright parts of the structure. So we've got the parapet at the top, which runs across the valley, and then we've got the piers beneath. And you bring the two things close to one another, and that helps to make the structural beam, which you can see in that image is really deep. It helps to make that recede a bit because you're pushing the bright parts out in front. So it's a kind of visual trick. You know, the sort of thing that Renaissance painters used to do a lot with the dark and light in the paintings. How am I doing for time?
10 minutes.
Okay. We'll go quickly through this one. This is another viaduct which some of the people in this room will recognize it. Do you want to talk about this bit? So we were really lucky to be working on this structure with Como and Perret and Paul Van Hagen. This is the next viaduct north of the previous one. You can see it's following some of the same principles in that it's a composite structure, but it's in a very different setting, even though it's quite close by. It crosses a road, a railway, another road, all in a really tight space, and it does it at a really pronounced skew angle, which means that we've got longer spans. This thing is not about the appearance and elevation as Wendover was, because it's sitting in this kind of hollow in the landscape, a little knot in the landscape, behind screened by trees and the rest of it. But in close to, the public road, which is a very busy road, goes underneath this structure. So the appearance of this thing close up and in the oblique view is really important. What was interesting is the contractor wanted to be able to launch his deck with his formwork in place. So at Wendover Dean, the deck is launched, or sorry, the beams are launched, and then a formwork traveller goes across it to install the deck on top. Here, he wanted to be able to roll the deck out with the formwork in place, so he could quickly put a slab on it and then use it as a haul route, which is a kind of construction issue, but from our point of view, it's a great opportunity for working with cantilevers in order to achieve that. So working with yourselves to achieve that ends, and it means that you have a structure which is should go again. Really kind of expressive in the detail. Now this hasn't come from a kind of some sort of abstract idea or something that's not related to the place or the structure. This has come from a requirement of the structure, and yet this is what provides the kind of the key aesthetic of the viaduct. So then the third viaduct that I was going to talk about is just to the north again, very different landform. It's so low to the ground, it's really an elevated causeway rather than a viaduct in a way. You can see the cross-sectional form is very different. And without going into the whole kind of story of this particular structure, what's interesting about it is that the entire thing is prefabricated. So it's an entirely precast viaduct. So it's 1 kilometer long, and every single component is precast and brought to site like a gigantic Lego set. So there's very, very little by way of in situ concrete work on this structure. And you can see some of the visual things that we've been doing with the other structures are also at play here, in particular, the way in which the pier projects past the bearing, that masks the bearing. You can see the piers arriving on site last year. And again, this form isn't just willful. It isn't just about doing something that looks nice. That projection has a piece of timber, sacrificial timber, stuck to it during construction, so that as the beams get lowered in, this forms a guide to push the beam onto its bearing. That makes sense? So that in so doing, it removes temporary works from it. So it's again about simplifying the construction process. So the viaduct itself helps to build itself in a sense. Oh gosh. It's not my holiday snaps. So this is actually, I'm going to do my bit for the Scottish Tourist Board. So this is the view from our studio in Scotland. And talking about landscape and those previous viaducts, landscape is how we also approach buildings as well. It's the most important consideration. You have this incredible landscape in the Cairngorms. It's like a bit of subarctic tundra, sort of ships across from Scandinavia and drops onto the UK. You've got sublime, so in the Victorian terrifying sense, absurdly picturesque, to kind of chocolate box. And we've got a building, our studio sits in amongst all of this. So what does it mean to position a building in this kind of location? Well, it means exactly the same as to position a viaduct in the Chilterns AONB. These are very precious landscapes. They're under pressure the world over. So to do any development in these kind of locations, you need to be really thoughtful and considerate as to what you're doing. So here we're really using the form of the landscape to drive the design of the building. So the studio is actually in a disused quarry. So it's in a brownfield site. And we're taking the contours of a quarry and using that as the generator of our plan. So you can see the elements of our building coming together. These are 2 chimneys for fireplaces. So they're almost like the piers of a viaduct. You can see our studios at one end, and then we've got a public cafe at the other end. And then the building kind of is built up around this kind of armature that, like I say, is derived from the contours of the site. So it's a really kind of beautiful place to work. Very kind of calming atmosphere. And like I say, it used to be a quarry, so it was full of really badly contaminated land, even though it's surrounded by this beautiful woodland. We've cleared up the contamination. We've got the pond in the middle, and the way in which we then seeded it, and we've got trees and what have you that have come in. So it's now an extension of the natural landscape around it. And again, there's a lesson there in bridge design, because as bridge designers, we're always thinking about the landscape around it. It doesn't matter whether you're an engineer or landscape architect or whatever. It's always about the setting as much as it is the structure, and how things kind of connect to that setting. I'll skip through these because this just talks about how the building mass is quite a big building, but you'd never really perceive it as such a big building because you look up the roof and you'd never get a feeling for how tall it is. There's another video of it. So because we have the cafe on site, this is obviously a very quiet day. Normally, the cars are like double parked and there's hundreds of people queuing up for coffees and whatnot. And they all come wandering around our building because it's kind of an open site. So we'll be working away on some nice bridge somewhere, and there'll be people at the window peering through like this, and then people go up onto the roof terrace at the back and they're peering down at us like this. It's like we're in a kind of goldfish bowl. But no, it's a lovely place to work. Back into bridges, because that's kind of why we're here. We have done some bridges in Scotland as well. So this is in the foreground. This is the Ganshiel Bridge, which was built in 1750. It's a scheduled ancient monument, listed building, really kind of precious structure. It was built by, I don't know how much of you know about Scottish history and the Jacobite Rebellion. This is what Scotland. Huh? Outlander. There you go. So the baddies won, and they built this bridge to keep the Scots under control. And it's a really cool, I mean, you can see the arch. It's a gorgeous, gorgeous bit of masonry. And our new bridge is basically taking all the vehicle traffic, because that was designed for horse and cart and foot soldiers, and not buses and lorries. So we've built this new bridge alongside to divert the traffic. See in the foreground there, and then the old bridge is now a kind of almost a museum piece. It's for tourism. So look at this beautiful thing. Very happily, we've got very active and active neighbours who are really interested in architecture and design in the King. So he opened the bridge for us last year. That's a kind of a segue back into bridges. I wonder if.
Do you want me to chit?
Yeah,
I mean, they're on a roll, but this is one kind of close to where we live, central London, just north of King's Cross, part of a big development. And in this case, is this, well, you'll see, if we have time, you'll see this, the kind of first bridge in the development that we worked on. But this was the second one where a client had asked us to do a relatively modest bridge that was still something that would draw people's attention. So in a way, it's kind of, I guess, economy of action, but something that it basically allowed us to use a really simple form, so a truss, but because we knew it needed to be expressive, we boiled it down to the specific details, or the kind of really refining one module and then repeating it along. Let us look at, you know, how every single part of that module is working as well as it could. So expressing the compression members, expressing the tension members, angling the plates in a way that was working with the loads that they were dealing with. So we ended up with this really efficient thing that was also quite sculptural, and it stands out and it gives them what they want. And it was just a lovely piece of design, being able to get, like, from the get-go, we knew we wanted to get really into the details and the way it was built, it was installed. And then I think, like, the next level was how it contributes to the urban realm of the area. So what you can see, those green steps in the background are a place where people come to watch events in the summer on a big screen. So you get people kind of congregating by the canal, and then this bridge forms kind of like a side balcony where you can get more people watching the event or watching. It's great for people watching, and it gets really busy and lovely there in the summer.
Yeah, I can
You're doing both for me.
So this is the last of our three kind of economies, as it were. So economy of material, which is the most kind of obvious one in a way. And again, I'm going to be a bit of a cheat and use not a bridge to talk about it, because it is all just design ultimately. This is a competition that we won. Well, this isn't, but the next thing is competition that we won for a new type of OCS, so the overhead catenary system, or the overhead power system for an electric railway. You'll probably recognize this. This is a French system, but they all look the same the world over. They're kind of a, you know, Meccano up in the air, hanging from wires with ceramic pot insulators. And this is a competition to rethink an OCS, to see if there's a better way of doing it. So we sort of took the view that actually all it's about is the position of the copper wire that carries the current to the train. That's the most important thing. Everything else, all that paraphernalia up in the air, is in service of achieving that. That wire needs to be at a very specific place for the train to get the current from it. And it needs to zigzag from one mast to the next, because if it didn't zigzag, it'd be like a cheese wire that would cut through the train's pantograph. But beyond that, it's very simple. It's just geometry. And if you approach it in the same way that we all approach bridge design, it's a geometric problem first and foremost. How do you achieve this solution? So you can see the SNCF system from France, and you can see our system, which is 25% shorter, gets rid of all of the clutter. There's, again, to sort of reinforce the point, as we switch through, you can see how much simpler our design is. Now, we use the same sort of individual connection componentry of standard systems. So much like the fountain at the start, which can take any tap, this can take any type of wire attachment, whether it's in the US, or whether it's continental Europe or the UK, any registration arm. These are some of our patent drawings. So we've got the connection at the back of the mast is patented. And then you can see there's one of our prototypes. We've got several prototypes. One's in our office in Scotland. The others are in testing yards throughout the UK being tested on railway. Now, the advantages of it are a 25% reduction in height. Because we don't need the tension wires and what have you to keep this thing up in the air. A 10% reduction in area. Again, same sort of numbers when you're looking in the elevation. But this is the really main one, 70% reduction in part count. So all of those bits and pieces that are doing the thing on the left-hand side are replaced essentially with one component on the right, which is made out of what's called permalloy, which is a densified wood laminate. It's basically plywood, but it's plywood that's been impregnated with resin at a really high pressure. So it's got incredible electrical strength. It's a kind of wonder material of the same generation as Bakelite. It goes back 150 years, this stuff, but everyone's forgotten about it because its only use nowadays is in transformer housings in power stations where they get huge blocks of it, mill it out and stick the transformer in because it's strong and it's electrically strong. But otherwise, it's not got any application except for here. So we've used this material to form the component in our mast. And it gives you these incredible figures because it's essentially made of wood. You get a 75% nearly reduction in CO2 for just one mast. And then if you extrapolate that to the whole mast and then you run it across the whole length of HS2, you get this sort of incredible figure for overall carbon reduction. I'm going to skip the next bit. How do I do that?
Skip it.
Oh, yeah, you need to skip it as well.
So
That's really awkward, isn't it?
the durability of that material, I mean, so it can be exposed to weather and it doesn't expose or anything because it's a high resin.
Correct, yeah. So it looks like, I mean, it weathers like wood in a way, superficially. So the surface goes grey and it'll even like get lichen and stuff growing on it. But there are examples of this. There's actually a park bench somewhere in Switzerland that made out of this. And it's been sitting there for 120 years. And it's like rock hard, you know? So it's really kind of, it's a wonder material. It's a bit expensive, but it's not, but it's comparable. It's comparable overall. Let's get through these. I was going to talk about another building that we've approached in a similar way to the design of a bridge, but we'll skip through that. There we go. I'll let Ezra talk about some bridges in Germany.
Yeah, well, I think that the relevance of this one is it's a timber bridge in Germany, and the way we approach it is really similar to the way we work on buildings usually, and it's all about kind of protecting the materials, protecting the structural materials. So timber has a ton of potential in infrastructure design, but only I think if it's used in the proper way. It's not just used for the sake of using it. So in this case, we're lucky to work with some German timber bridge specialists, and they've taught us a lot of things. But clearly the first lesson is how do you protect the timber? How do you use the form of the bridge to protect the timber? So again, it's a half through structure, beams on the outside. But the way we've done it is we've oriented them leaning slightly outwards with a metal cap over the top and kind of almost building cladding on the inside. So you end up with this expressed glulam structure on the outside, clad over the top. The form of it is very much related to its span and its structural performance. It's also in a flood-prone river, so the structure had to be above deck. We wanted to make sure people didn't feel overwhelmed by these really deep beams, so that the pathway kind of goes up and over and responds to the shape of the beams responds to that as well.
That's difficult to keep track of one and the other.
And I think the other part of it is just understanding how these things are made, what the opportunities are in terms of form and structure. This is the second generation project we're working with the same team in Germany. And in this case, it's a timber concrete composite structure. So you've got the timber below shaped in the way it needs to be shaped to handle loads, but then the concrete above is actually what's protecting. It's protecting the timber, but then it's serving the double function of working as a compressive element at the top of the structure.
This is back to me. I guess this bit's kind of quite personal. So we've separated economy of purpose, economy of action, and economy of material. There's three different ways of looking at this, but really it's a bit of a conceit, because I think you could have taken any of those projects and swapped them all up and put them in any of the categories. Because I think, like I say, economy is an objective in its own right for all the work that I think we all do, actually, particularly now with the focus on energy use and carbon content. So I'm going to close on a project where I'm going to close my bit, and then Ezra's going to talk about something else a bit more current. I'm going to close on a project where these aspects are almost in balance, at least as far as I can see. Now this, sorry, this isn't the project. This is Metsovitkos, which is the very, very first bridge that I was ever involved with as an architect. So this is back in 1999. As part of the competition-winning team. There were only three of us on the team. This bridge in northern Greece. We were working with Wilkinson Air Architects that I was working for at the time. So it's Jim Air, myself, and then Angus Lowe, who was an engineer at Arup in London. Then there's me with Angus Lowe on the left and Ian Wilson on the right. Ian Wilson retired from Arup last year. Angus Lowe sadly passed away last year. And these two guys are basically my engineering heroes. And we're very lucky. The people we work with are all kind of geniuses, but these guys have had such a profound impact on my career. And the bridge we're standing on is the last bridge that I'll talk about, which is Somers Town Bridge, which is just around the corner from Ezra's red truss bridge. And the three of us worked on this structure together. Now, the genesis of it is actually a conversation that Angus and I had like 10 years beforehand, before this bridge was even an idea. And it was this discussion about how to do a bridge of extreme simplicity. Can you make a beam that's just simply an expression of the bending moment that governs the shape, it governs the form and the material? So it's using the least material, because it's just the bending moment, and then stiffening it in order that it doesn't buckle. So again, doing the least you can do to achieve this structure, but then doing it in such a way that you're concentrating on the detail, you're making all these things come together in a really sort of beautiful and considered way. And so this was the result. So 10 years on, we had a brief that came to us from Related Argent, the same people who did Hudson Yards here in New York. And this was our brief, was to design this bridge, and it was the perfect opportunity for this approach because it's in a historic setting. So you've got these Victorian buildings, Victorian structures around it. There's something of the Victorian attitude in what we were designing. You've got the canal, the perfect span. It's 40 meters, which means we can have a beam depth of 1.1 meters in the middle. It's working quite hard, this beam. But so you get this beautiful form, which is the parapet, it's the structure, It's everything all in one. It's using the least material. This bridge is thinner than my thumb in its thickness, but because of the way in which the stiffener is arranged and the top chords, it's a beautifully kind of stable and strong structure. Like I say, it just came from the bending moment. Skip through these. I think there's, yeah, so it's probably, it remains the favorite or one of my favorite bridges that the practice has worked on, even though it's very small compared to some of those other bigger structures. It's a kind of perfect expression in a way of this way of working and collaborating that we have. That's the end of what I think I'm just going to talk about, just very briefly about 3 bridges that, that we've got on the go at the moment.
It's almost like the bonus segment. So this is a competition. Actually, jury's still deciding, but this is a competition we've done in Oslo recently where developer client has basically building a whole new neighborhood or converting a neighborhood from office space into residential space. And part of that, they've identified there's a river running down the middle of the neighborhood, and they want to put in a couple, well, up to 6 or 7 bridges to really stitch the neighborhood together. They brought in a bunch of different architects to all look at different bridges at the same time. And we're looking at 3 in close proximity. And it's been a really wonderful exercise. Designing one bridge is always fun, but doing 3 at a time is actually a new thing for us. And it's really cool because you get to understand, or you get to think about relationships between the bridges, and between the bridges in the landscape. And in this case, we've kind of used the same design philosophy, but come up with 3 really different structures, and each one is related to its function and its location. So you've got one bridge which is working really hard geometrically. It's connecting 2 banks that are at one is much higher than the other one, so we needed extra length to get the ramps or to get the slope to work. So it's an S-shaped structure to work geometrically. It's also for cyclists, so it slows the cyclists down. Because it's doing that, we've gone with a steel structure, so a steel torsion box down the middle. And intuitively, we thought kind of getting over the water as quickly as possible was the right solution, but the client actually pushed for this unusual situation where the bridge actually runs kind of parallel right down the middle of the river, and then it kind of spans the banks as quickly as possible. And we've been able to achieve that through the careful location of piers and crafting the form. And then, of course, we top it off with this nice handrail that runs along and expresses the shape. So that's one of them. The second one, the one at the top is in this case, it's again connecting high to low, really kind of a straight shot, bringing users through the river valley at a high level. So it's almost a treetop walkway feel. And in this one, we wanted a really simple, slim, slender structure, and bringing the abutments out to meet the structure, keep the structure as like short as possible. In order to make it really slender, we've pulled the tension member out of it and underslung a cable along the bottom. So it's similar to that German bridge, but in this case, even more kind of longer, slimmer, more efficient. And the third and final one, totally deserved you. The third one is right in the middle, and it's actually the lowest of the bridges. So it's in the kind of flood zone. Needed to be really robust. It kind of beds in well with the banks at either side. It's around a bend in the river, so you've got asymmetry in the site. One side's the inside of the curve where it kind of gently comes down to the river, and the other side is steep. So we've taken all of that on board, and we've come up with it's like a segmental tension, post-tension stone bridge. So breaking it up into slices of stone, granite, stringing them all together, tensioning them up to serve as both the structure, but also the containment for vehicles. So it's really robust, lots of opportunities for shaping that we're excited about. The shaping will, of course, have to do with the structural load going through it. Containing users, something that's tactile, gives us a chance to play with structure and detail and all of that stuff.
That's so good price. So that we're wrapping up now. And I think the moral of all of this stuff, going back to that original quote, that you shouldn't be interested in design of bridges, is that actually all of us in this room are concerned with how to get to the other side. And I mean that literally, but also as a metaphor in terms of how we work together and pursue the design of these things. Thank you very much.
Thank you very much. That was excellent. Do you have any questions? Start with one. Go ahead. If you do have a question and you're at the table, please pop the microphone so that. Yeah, there you go.
This is probably a bit of a local question for based on experience of London, but the Victoria Dock Bridge.
Yeah.
In the plan you showed it was right next to the existing Victoria Dock Bridge.
Yep, well spotted.
Yeah, well, I used to cycle past there all the time.
Yeah.
But it's quite the existing Victoria Dock Bridge. For anybody who doesn't know, it's a stay cable bridge. It's of quite an unusual design, but it's quite high level because they built it on top of elevator shafts, basically to give the clearance for like super yachts and stuff that use the dock to get up and down. Was there any? It just seems a little bit incongruous in terms of the carbon emergency that you've got an existing bridge here already,
Yeah,
and then you're building a brand new bridge right next to it.
absolutely.
Was there any consideration given to reusing that structure or
Yes.
improving access?
Yes. Sadly, it was that structure. I mean, Lifshitz Davidson, who are the architects, I forgot who the engineers, Bureau Apple, I can't remember. I can't remember who the engineers were, but they're not in the room, so I can say this.
Mhm.
That bridge is absolutely not fit for purpose in its the current requirements of the bridge. I mean, it was fine when it was built because it only had tens of people crossing it a day. But the development at Silvertown we mentioned it's going to have thousands of homes in what's currently a derelict part of London. And then there's a new station to the north as well. So the bridge needs to cater for tens of thousands of people a day rather than tens of people a day. And the Lifshitz Bridge has the elevators which keep breaking down. And you've got the stairways and all the rest of it. So if the elevator's not working, then people who aren't necessarily able-bodied can't use the bridge. There are so many problems with that structure. The deck is very narrow, so even if you could guarantee getting people up to it, you wouldn't have the capacity. So our bridge, in fact, started off at 5 meters wide for capacity, but we did additional capacity modeling with Arab that suggested it needs to be 6.
About 6, yeah.
6 meters wide. So we're talking an entirely different brief. But I agree, on the face of it, 2 bridges next to each other does seem a little bit odd, but.
And I think we've talked about moving that bridge or reusing it somewhere that makes more sense, but I think there's so much underground for that structure. It's not a simple pick up and move bridge. But actually the one nice thing is at the ends of our bridge, there's going to be signs saying it's about to open. And if you're in a hurry, go use the high level bridge to bypass it because it takes about 10 minutes to open and close. So it will serve kind of an overflow function at times, but yeah.
Okay, yeah. Thanks for that.
It's a really good question, though.
Typically in the UK, is the architect commissioned first, the engineer, or is it typically a team, or is there a forced marriage at some point? How does it typically?
So in the best instances, it's a team, because it being a team actually reflects the way in which the process occurs when it occurs well. The King's Cross bridges, so the red one and my favourite one, the architect was appointed, and then Arup were appointed secondary to us. But that's unusual. I think normally we will be a sub-consultant to an engineer. I'm very happy to be sub-consultant to an engineer. But best instances are when you go in as a combined team and win the commission.
Anyone else? I have one more regarding the precast segmental bridge. There were a couple of them, I think, or at least one. Am I correct that there was a moratorium of sorts on that type of
Yes.
bridge?
You know more.
Yeah. So Tame Valley Viaduct, the one that I described as Lego.
Yeah.
Yeah, exactly right. So in the UK for quite a long time, there's been a moratorium on that type of connection, which is why that technology has advanced in, for instance, Spain so well in recent years on their high-speed rail products, but nothing has happened in the north of Europe. And it's basically to do with de-icing salts on the road. And because it's a railway, it's a long way from a road, there aren't going to be any de-icing salts. So that has enabled that scheme to be progressed. But that's the reason. You're quite right. There is a moratorium, or has been.
Yeah, I think there was a detail with the cables, and there was some bad detail that was addressed.
Yeah.
So let's,
Yes,
it's acceptable.
you're exactly right. Yeah. Exactly.
Evolution of technology.
Yeah, exactly. And understanding, changing, shifting requirements as well. Yeah.
Could you just talk a little bit about the process of conceiving the concept and then having the dialogue or the relationship with the engineer,
Yeah.
and how critical that is to have?
Super critical. So, that's kind of goes to the absolute heart of it. And I just sort of mentioned in passing that I don't really like talking about disciplines, particularly architects and engineers and all the rest of it. I mean, yeah, we have our own responsibilities, and there are liabilities and kind of areas of expertise, absolutely. But ultimately, we're all in this world. We're all kind of bridge designers, so we're all looking to achieve the same end ultimately, which is a really good bridge. It's perfect for its location and its use, and etc. And I've had conversations with structural engineers, notably a guy called Paul Sanders, who's a partner at Covey in London, where Paul has suggested ways of looking at a structure from an architectural or an aesthetic point of view. And in the same conversation, I have had suggestions to him as to how this structure is going to stand up. I can go into detail about it. We talk about it whenever we meet. It was like a complete role reversal, but it was totally unself-conscious. It happened because we're just working around a table, and that's the best situation to get in. I mean, if you rewind in history, separate disciplines for architects, civil engineers, structure didn't exist. There were, I don't know what they called themselves. They probably called themselves architects at the time, but it was all combined. Thomas Telford, the great Scottish engineer who built, hundreds of bridges in his lifetime, started off as a stonemason, then became an architect, then civil engineer, but civil engineer only just became invented pretty much by him in his career. And then he went back to bridges, construction, all the rest of it. But there was no difference for him. It was just part of the same kind of continuum with design and what have you. And so the best bridges are where you can't tell whether an architect has been involved or not, really, where it's just invisible.
Are there any questions online? We have about 20 or so people. If you have any questions, please speak up.
One is Ezra, your project with stones post-tensioning system. With stones,
Yes.
It's very interesting. It's new technology, I think, never seen before. Are you in touch with any designers doing that, or just are you getting any support from some specialists there?
Well, we are again working with Covey on that one, but and they have a couple people who are looking into stone. I think there are some examples of it being
Already done.
No, there's
For carbon footprint, it's brilliant.
Yeah.
It's amazing. It's a beautiful idea. I like it.
I think it's also in a location that has good stone.
Amazing.
So the quarry, we're not bringing in stone from China.
So 1 point for you on that. But on the other one, I want to know, you got on the bridge in Scotland.
Yeah.
With very nice idea. I don't know, Jim, what does think about that bridge? I was expecting to comment on that bridge. The lift, the
In one in Dublin.
in Dublin, yeah.
It's
It's
like
very-
Dublin, Ireland.
So
Or is it?
it's have you got any carbon management in place there? Because I think with 4 turnions, right? Why do you want to have 4 of them? More maintenance, more material. The idea of having one head that turns, it's very easy.
This is also a brilliant question,
Yeah.
because you get to the heart of it.
So you got the good thing with stones, but I'm really curious to know why you got. It's fine, 50.
There's a spar.
Yes,
I mean,
like you're really putting us on the spot.
No, I mean, no, just interesting and very, very interesting. But
well, the spar one is really interesting because we actually questioned it ourselves and we wondered, and I mean, this is stuff you guys must do all the time, but if you look in the future to the cost of electricity and the cost of energy, and you compare that to the investment in material up front, it's actually really close. Like if with no counterweight, you just push harder. Over time, it was actually gonna break almost even, but then you brought in the client and their need for something interesting, and I think that kind of just tipped the balance towards doing a counterweighted structure.
No pun intended.
And yes, there are more moving parts, but they're relatively off the shelf moving parts. So they will require maintenance and no replacement, but we thought overall it actually was more efficient. If you're going to do it, try to do it as efficiently as you can and make the most use of that mass to do the lifting as we want to.
Okay, well, thank you very much. Thank you, Ben.
Thank you. Thank you. That was really fun.
Thank you, everybody online.
Thank you. So we got those.
I have full confidence in you.